Nuclei are the hard nuggets at the centers of atoms surrounded by the cloud of electrons. Nuclei are made up of protons and neutrons and are described by a few different numbers. The atomic number, which is represented with the letter Z, is the number of protons in a nucleus, and the neutron number, which is represented with an N, is the number of neutrons. The mass number tells you the total number of particles that make up the nucleus, so it's the number of protons plus the number of neutrons. An element like zinc or gold or hydrogen always has the same number of protons but can have different numbers of neutrons. So a single element with different numbers of neutrons, these are isotopes. So by specifying the isotope of an element, you're saying how many neutrons are in that particular element. So nuclei are written with typically the following notation. There's the chemical symbol for the type of atom we're looking at. Then there's the mass number, the number of protons plus neutrons, divided by or over top of, so there's a superscript and a subscript, and then the subscript is the number of protons. So for example, carbon has always 6 protons, so for carbon you'll always see a subscript of 6, and then the superscript is the total number of particles. So for carbon 12, there are 6 protons and 6 neutrons to add together to give 12 total, and for carbon 13, there are 6 protons and 7 neutrons. And sometimes, since the chemical symbol already tells you how many protons there are, sometimes the number of protons is left out, and you just refer to an isotope by its mass number, how many total particles it has. Now hydrogen, it turns out, has 3 isotopes, and the 3 isotopes have their own names. So typically when someone says hydrogen, they just mean hydrogen 1. They just mean hydrogen with just a single proton in its nucleus. If the hydrogen has a proton and a neutron, it's referred to as deuterium. And deuterium is the hydrogen that occurs when you have heavy water. So if you've ever heard someone refer to heavy water, what that means is that at least one of the hydrogens in the H2O is a deuterium. Tritium consists of 3 particles, so 1 proton, 2 neutrons in the hydrogen nucleus, and tritium is radioactive, so that kind of hydrogen will decay over time. Now, just as a reminder, of the 3 particles that make up atoms, the proton has a charge of +1 fundamental unit of charge, +1 e, which is equal to 1.602 times 10 to the minus 19 coulombs. Electrons have the same amount of charge but negative, and neutrons have no charge at all. A mass spectrometer can be used to separate different isotopes of a particular element. So the way a mass spectrometer works is that you put a sample in one end, and then if the sample is not already gaseous, there is a heater that vaporizes the sample and turns it into a gas so that it can be accelerated. So the gas not only is accelerated, it's also ionized so that it can be accelerated by an electric field. So you have a potential difference between a couple of plates, and that accelerates these ions. So at least 1 or more electrons are stripped off so that it can be ionized, and then it can be accelerated by this electric field. And then there's a magnet. Now, of course, the magnet will cause these charged particles or these charged atoms to have their paths bent. And then if you look at the amount of bending, that tells you something about the mass, because the heavier atoms will be harder to have their paths bent because they have more inertia, and so they'll end up on one part of the detector, whereas the lighter elements will, of course, be deflected more and end up in another part. So if you then look at how many atoms make it to the different parts of your detector, then you can describe their relative abundances as a function of their mass divided by their charge. Now, knowing about the different isotopes is useful even in the field of biology. It turns out that certain plants will preferentially use different isotopes of carbon. So if you know the ratio of carbon-13 relative to carbon-12, these are both stable isotopes. So these are both isotopes that do not radioactively decay. If you know the ratio of those two isotopes of carbon, then that tells you what kind of plant you have. And additionally, nitrogen-15 tends to have, relative to nitrogen-14, tends to have slightly more abundance the higher you are in the food chain. So you can take samples from different creatures or from maybe some bone samples or what have you, and look at the relative ratios of different isotopes of different atoms and tell something about the diets of those animals. So for example, nitrogen 15 being more abundant the higher you go in the food chain. You can kind of see that happening here. So these dots represent terrestrial ecosystems, and you can see that herbivores are lower in nitrogen-15 than omnivores, which are lower than carnivores. So the higher you're going within this ecosystem, then the higher you're going in nitrogen-15, the higher you are on the food chain. Likewise, in the marine ecosystem, shellfish are lower than fish, are lower than some more carnivorous fish, and then marine mammals, which eat the fish, are higher still. Then also on the horizontal axis, we have the relative ratio of carbon-13 to carbon-12, and that can also give you additional hints as to the sort of environment and the types of plants in that environment. So here we have the equation that's actually used to calculate this change in carbon-13 ratio. So basically the way this works is that you take the ratio of carbon-13 to carbon-12 in your sample, and then there's a standard that you're comparing it with, and then you subtract 1 from that and multiply it by 10 to the third in order to get the numbers that are plotted on this axis. And you do the same thing with the nitrogen ratios.